Good morning, everyone. It is my great pleasure to be able to talk to you today about a future memory chip that combines memory and compute. My name is Sydney Tsai. I'm from IBM Almaden Research Center in San Jose, California. The title of my talk today is Analog Memory-Based Techniques for Accelerating Deep Neural Networks. The outline of my talk today, I'll first give an introduction of the workload that we're trying to accelerate, namely deep neural networks, and how that maps into analog memory. I'll then use phase change memory as an example to see how we can implement with today's memory DNN training and inference acceleration. We'll discuss the energy efficiency benefits and in general, what are the design considerations outside of the analog tiles for such analog-based techniques. Finally, I'll give a summary. The rise of AI and deep neural network relies on three pillars: the algorithm, the data, and the hardware. The algorithm has existed for a long time, but it was not until the data, which was ImageNet in 2012, and the hardware, GPU at the time, what became ready. The deep neural network has since become a major field of AI and has demonstrated superhuman accuracy in several tasks, including object detection, speech transcription, and language translation. Many of these models has outperformed role-based models. Even though remaining a black box, it has shown to be a fundamental building pillar for the recent era of AI. So let's take a look at the hardware pillar in the three major components. What is the hardware that's used today? The most generic hardware remains CPU and GPU. When talking about what hardware we use for acceleration, there's a trade-off between flexibility and speed. The emerging new class of hardware includes custom digital accelerators, so ASIC chips, that applies a number of architectural changes that's customized for deep neural networks, or applies approximate computing, such as reduced bit precision from floating point 32 to floating point 16, or down to floating point 8, 4, or int 4, or int 2. While that trend continues to improve the efficiency of current hardware, we believe that in the future, another type of accelerator is very promising. That's the type of hardware we're going to talk about today, the analog-based accelerators. If we take a closer look at what we are trying to compute here, the deep neural network consists of layers of neurons connected by synaptic weights. Each synapse carries a weight that is multiplying the input activation from the neurons and accumulated to downstream neurons. When a network is initially untrained, all the synaptic weights are random. When a training image, such as a number 7, is brought in, so each intensity of each pixel is mapped into the activation strengths of the input layer, the activation will propagate through the multiple layers and generate output neuron activation strengths. Initially, the strengths, the output neuron will be equally, the strengths will be equally high. This means that the neural network doesn't really know what the right answer is. It is through this labeled training process that we tell the network that this is a 7, so 7 output should be 1 and everyone else should be 0, that we can backpropagate the error through the output of the layer back to the initial layer to update all the weights. And through this update stochastic gradient descent training process, the weights will become trained. And eventually, when we do forward inference with the input image of 7, output will only have a high signal at the 7 neuron. The hardware opportunity we see here is the acceleration of this box here, the vector matrix multiplication. So we'll go a little bit in more detail how we envision mapping this workload into hardware. So what is the fundamental idea for this analog memory-based acceleration? What is it that we're trying to avoid from current digital architectures? So in today's digital architecture, you will have a compute unit and a memory unit that is separate. When you want to, say, multiply two numbers, A and B, The compute and memory unit is connected through a bus. This is referred to as the von Neumann architecture. You will bring this A to the bus, to the compute unit, and then the B to the bus, to the compute unit. We will produce the result at the CPU, and then send the results back to memory. The challenge with this is that as technology scales, the compute unit and the memory unit continues to improve. However, the improvement in the back end is very limited. Therefore, the bus energy and also the bus bandwidth is not increasing as quickly as the compute and memory unit. This means that a lot of the more and more of the energy is consumed in the data movement. And also the bus bandwidth could become a limitation unless you go to a very expensive high bandwidth bus communication scheme, or you bring the memory on top, which also usually increase the cost of the overall system. So what are we trying to do? We're trying to combine this memory and the compute unit. Envision an analog accelerator where we have A already stored in the memory. We will then bring the multiplication number B into the memory and produce also locally the output C. We then send the C out directly to the output. And there, we do not use a bus, and the compute is done inside the memory. We see this as an opportunity for better energy efficiency and also higher throughput. So the question is, what kind of memory architecture would this be able to, would allow us to map this type of workload? So what we are relying on here is the help of physics. A typical way to map this problem of W times X multiply W times X and accumulation is to use a analog crossbar array as shown in the right. Each weight here is mapped into a pair of conductance, a G plus and a G minus. The reason why we usually use a pair is to be able to represent both positive and negative weights. So the net weight is the difference between the two G's. We then bring in the X in two forms as the voltage. So it can be either the analog voltage or a time duration with analog or a binary voltage with an analog duration. So the current based on Ohm's law is going to be proportional to the conductance multiplied by the voltage. So Ohm's law will help us produce the multiplication. The next step is to do the accumulation. So after the multiply, we accumulate by collecting all the current across a column. So the voltage is applied across the rows and the current is accumulated across the column. With this scheme, either we sense the instantaneous current with the analog instantaneous voltage, or we accumulate the total charge if the voltage is an analog duration. So the sum is also performed using Kirchhoff's law. We can then apply the nonlinear function at the output neuron at the output neuron to get the final output Y. So if we look at this crossbar array, the memory array itself is identical to the memory array we have today. What needs to change is the neuron circuitry and how we process the signal, and the fact that we need to simultaneously activate multiple word lines instead of one at the time. So what are the possible memory options for the crossbar array? The answer is that this remains a very active research area of research. So none of the existing memory is truly ideal. And also because the fact that analog computing is intrinsically difficult, that's why most of the memory today remains digital. However, many of the candidates shows very promising characteristics. So today we are going to focus on phase change memory. And here is the reason why. So phase change memory consists of two phases. One is an amorphous phase that has high resistance, so low conductance, and a crystalline state that is lower resistance, so high conductance. The way we switch between the two is by applying different types of pulses. the pulses that's applied, in this case, a high voltage pulse will locally generate a lot of heat around the very small back bottom electrode and melt the phase change memory locally to create a amorphous phase. By applying a lower voltage pulse gradually, the lower level of heat will allow the amorphous phase to gradually crystallize back from the outside towards the bottom electrode. We've shown that this process can be repeated many times, and the conductance modulation range is very large. So the main reason that we choose to use phase change memory to develop this technology is first that the technology is relatively mature. There are large-scale demonstrations in the lab and also products using phase change memory today in the market. The second is the large resistance contrast. And the third is the high endurance that compared to especially flash, that we can switch back and forth between the two states many, many times. Finally, even though phase change memory still has some non-ideal characteristics, there are good physical understandings, and thanks to the large arrays that we have, we are able to characterize and understand the behavior. So we will talk more about the non-idealities in today's talk. So let's see how we use phase change memory for deep neural network training and inference. So starting with training, the process of training, as we shown at the beginning, requires fine-tuning of the weights over many examples. So for each example, the network weights need to learn what is the right direction to move based on the current example. So what it needs is very gentle and symmetric conductance change, which most of the analog memory suffers to do. So an example here shows a phase change memory device with a typical conductance versus number of pulse characteristics. So if you fire more pulses, it will initially have large conductance increase and then gradually saturate out. So the phase change memory has several problems, including that this change is only unidirectional. You can only increase but not decrease. Each pulse is stochastic, and the curve is not really linear. So even with this type of characteristic, we have shown in 2014 that the deep neural network is so resilient to noise that even with this type of update, we can achieve 82% accuracy on the mixed hardware in the mixed hardware software experiment on the MNIST data set. So the hand digit recognition data set that asks you which digit basically this image is. So you can achieve not 98%, but 82%. So it is better than much better than randomly guessing with this type of hardware. In 2018, what we show is that with a new unit cell design, we are able to get that 98. So here is how. The key there is to not use the phase change memory as the training element for the weight up and down. Because the up and down is too nonlinear, we use a linear memory that we all know works very well, which is the capacitor. So we use a new 3T1C, 3 transistor, 1 capacitor cell, where we add and subtract charge from the capacitor to modulate the weight that is read out from the readout transistor. So the readout transistor conductance is the weight that we read out in this scheme. So during the training process, what happened here is that we will apply all the update pulses to the small g's. So the g minus is shared, and g plus is the active element. So we will either add charge or subtract charge from the small g plus. And then only once in every 8,000 images, we will transfer the net difference between g plus and g minus to either g plus or g minus to store the weights in a non-volatile memory, in this case, phase change memory. The advantage of this cell, first of all, it is now symmetric because of the symmetry in the capacitive device. It increases dynamic range because we can add a F factor here between the non-volatile memory conductance and the capacitive conductance. So the effective dynamic range increases. We preserve the non-volatility because every once in a while we will transfer the weights to the phase change memory. And also we've shown that with the CMOS, even with CMOS variability, we were able to develop a technique called polarity inversion, which we switch the PFET and NFET roles every 1,000 images, so that the even if NFET and PFET are not perfectly matched, we ensure that the increase of the weight and the decrease of the weight over time is going to be balanced. With this new unit cell, we were able to show that MNIST, so the blue line is the training curve, the orange line is the test curve in experiment, well, with the gray line being the simulation curves in TensorFlow. We were able to show that the MNIST is at software equivalent accuracy for tests, and also MNIST with background is also near software equivalent accuracy. We further show that another type of data set, which is a little bit larger and also more common use case in edge training, that if you do transfer learning, we can also achieve software equivalent accuracy. The way the transfer learning works is that you will pre-train a large pre-processing usually convolutional networks with a larger data set. In this case, the network we use is Inception v3, and the Inception v3 network was pre-trained on ImageNet. So the pre-trained network will process the real image that you are classifying right now and produce a filtered vectors for the final classification. And it's only the final fully connected layer that we train in hardware locally to adapt to the current task in question. We were able to show that if we train this fully connected layer with the 3T1C plus 2PCM cell that's shown on the previous page, we were also able to show software equivalent accuracy for CFAR 10 and also CFAR 100. So switching gear to inference. For inference, the requirement for memory is very different. Now we do not need to fine tune the weights very frequently. Instead, we want to get to the target weight in multiple shots. So we want the weights to be as accurate as possible. We'll pre-train the weights and we can apply many techniques as needed in software to train the weights, but we want to be able to program the weight in PCM as close to the target weight, and also have the weights stay there over time. So high yield, precise tuning, and no change over time. We have shown in 3 papers in 2019 and efforts towards how to make this precise tuning work. The first one focused on the programming scheme, especially when you have multiple memory devices in one unit cell. The second one shows that we can reach software accuracy using a long short-term recurrent network demonstration. And the last paper discussed about drift. So I'll go through the concept one by one and show how they connected to each other. So first of all, why do we care about the programming? So in a lab experiment, you can always go through one memory device at a time and try to program the memory as accurately as possible and take as long time as needed. However, if we are talking about designing a chip and programming the conductance in an analog fashion in a relatively reasonable closed loop tuning time, then what we really need is a more parallel programming scheme. So what we propose here is a row by row programming scheme. So the challenge here is really device variability. So when we program a device using a certain pulse, it is not guaranteed that the device will every time reach the same conductance. So we may need to try many times, and we may need to adjust the strength of the pulse that we apply. So here we show a case where a typical unit cell that consists of 4 memories, we propose a programming strategy that starts from the biggest big G's, so big G plus, then big G minus, then to the small G's. In this case, all 4 devices are phase change memory. So this is not for training, so all 4 devices are phase change memory. And the row by row programming algorithm here is a iteratively program that allows a participation bit. So you have a participation bit that determines whether the current phase change memory conductance is close enough to the target. When it is close enough, the participation bit is turned off, and then it is excluded from the next programming. If it's still far away, then we will continue to try, even with the same programming condition to give it more try, or we switch to the next either more aggressive or less aggressive programming condition to try to close the gap between the target conductance value versus the readout conductance value. So what we see is that using a realistic phase change memory model, we were able to show that the error will gradually decrease as we progress through the programming phases. And the final actual weight and desired weight correlation is quite tight. So talking a little bit about what are the type of pulses and the strategy that we can use to tune the analog memory. The first most intuitive programming method is to use a constant current pulse. So similar to what we show in training, that you can fire a pulse with a constant current, so constant compliance current, and just increase the number of pulses. So as you increase the number of pulses, eventually the conductance will increase. So we do see that the cumulative distribution function of the conductance gradually move to the right as we apply more and more pulses. The challenge with this technique is that the conductance does initially increase very steeply, just like the figure we showed before, but then it will quickly saturate to a value that is only dependent on the compliance current. So with a different compliance current, you will get a different saturation value, but within the same compliance current, if you apply multiple pulses, it will quickly reach within like 5 pulses to the saturation value and then just stay pretty much flat. So one intuitive knob here is to use this compliance current as a knob to be able to go to adjust the conductance more effectively. So another programming scheme is to just increase the compliance pulse, compliance current. So as you fire more and more pulses to try to get to higher conductance, you will not only increase the number of pulses, but you also increase the current for programming. So this does push the conductance distribution to the right too, but notice that there is this turnaround point that brings the conductance back down. So what is happening here, if you see the compliance current will increase and the conductance of the device will increase up to a point, because this is a transition point where your current becomes too strong that instead of crystallizing to bring the conductance up, it starts to amorphize it again because it's too hot and it starts to melt. The challenge in this case is that this turning point also varies from device to device. So it is difficult to say that I'll just continue to increase and stay before this point because some devices may turn down at a higher compliance current and some may already start to melt at a lower compliance current. So the curve can become monotonic and the transition point of the monotonic point varies from device to device. So in the end, what we decide to do is the decreasing scheme for applying pulse. So instead of starting from the low compliance, we'll start from high compliance. So we will be melting with the very high compliance current at the beginning. And as we decrease the compliance current, we will be melting less and less and causing the conductance to increase monotonically in this fashion. So you see a nice monotonically increase in the conductance distribution with a spacing. So here, this is very tightly distributed. And here, the spacing is much more equal as we apply multiple pulses. So this shows that you can also further tune another knob that we're not going into detail today, which is the duration of the pulse. So the longer duration, you also tend to push the conductance up slightly. So how does this actually work? So combining the pulse programming scheme and the participation bit, we are able to give a target conductance, in this case 3 microsiemens, and show that for 2 to the 16 phase change memory devices, we can shove most of the device into this range within a reasonable number of programming pulses. So that each device will get decreasing compliance current pulses. And then when they reach into this range, it will be excluded from the next the next programming pulse. And with this, we show a cumulative distribution function with various conductance targets, and some of the CDFs are very straight, especially for the lower conductance range. So that was conductance programming, and now we want to introduce the concept of weight programming. So conductance programming, we try to get to as accurate as possible. We try to get it as accurate as possible. Now we want to talk about how conductance map to weight. As we showed a little earlier too, that we propose using 4 conductances to be able to get the dynamic range and also be able to get the resolution that we need with today's PCM for the inference application we need. So here the big G plus and G minus also has a F factor between the two. And here we decide to divide by F instead of, to get the resolution instead of multiply by F. Because overall, this weight is proportional to the current that we will get, and dividing will bring the total current and also power consumption down. So in reality, we do the divide rather than the multiply. So what we see here is that this figure in the middle is what we shown in the last page, is as good as we can get for conductance programming. However, when we do weight programming, we have much more knobs to tune, because now you have multiple devices that you can iteratively program. And so in one case, if the first device is not strong enough to reach your conductance target, you still have a second chance of using the small g plus to reach your conductance target. So what we see is that when we use multiple PCM devices to represent one weight, the conductance programming noise in the curve is greatly reduced, and also the saturation is pushed out a lot further, and the range of straight CDFs increase. So with this, we try to see what this means for deep neural networks. So the deep neural network example we try here is long short-term memory. So what is long short-term memory? It is a recurrent neural network that takes an input at every time step. So the input is a function of time. And at every time step, it will have an internal memory and also an external output every time step, so that when you keep the memory, every time step, the output does not only depend on the X, but also depend on the internal memory, which is dependent on the previous X. So this type of network is very popular in sequence to sequence processing, such as speech recognition or translation. So the reason why we choose this is, first of all, the application is very relevant to industry application. The second is because it is much more difficult with the recurrent connection than the MNIST dataset, classification dataset that we've shown. It's shown that this recurrence nature makes these network a lot more difficult to either train or to be able to inference accurately. So so what we do here is that we pick a very typical benchmarking task for the LSTM. So the task is to predict the probability of the next character of word. So an example here is that you have a book, a textbook with many words. You will encode each word, and then the task here is to try to predict what the next word is. So for example, the N should predict the next word should be so, and so should be predicting the next word to be it. You can imagine that the answer may not be like a single answer, so the accuracy can never be 100%. If it's 100%, means that you are literally memorizing the book. So the measure of goodness here is what we call cross-entropy loss or perplexity. So there is a chance, if you have a good chance of getting the output right, means that you understand something about the language and means that you're learning about the sequence. So what we do here is that for the LSTM layer here, we see that the boxes, the W and the U, these are the fully connected layers within an LSTM. So LSTM will have some recurrent recurrent loops in the activation, but all the weight blocks inside is basically fully connected. So we will map the fully connected weights into our crossbar array and process the activation in a recurrent way. So one nice thing about this type of task is that the training is supervised because you use the next word to train the current state to predict the next word. However, there is no labeling required because with a text, you already know what the next word is supposed to be. So this allows us to very flexibly train on different types of data set without additional labeling. So a very popular benchmark in this LSTM world is what we call the Pentry bank. So Pentry bank is basically a text that is collected from many bank statement, bank news, and so on. So it's talking about money and like revenue and so on. And this is a common data set to use to be able to tell how well you are predicting the next word. So the experiment we do is so-called mixed hardware software experiment, where we map the LSTM weights into real PCM conductances. So the conductance will then map into weight. And then we bring in the LSTM example, so the first word into the system. And then we process that activation through a software, simulated software. And then when it comes to the weight, the vector matrix multiplication is done in software. However, the weight matrix itself is read from the phase change memory. So we make our best effort to program the weights, but every time we do the inference, we read out the current weight. So there is going to be re-noise and also programming noise, and also all the possible non-ideal characteristic from the PCM. So all the activation is processed in software, but all the memory weight element is in hardware. So what we see here is that with a PyTorch perplexity baseline around 98, if we use two phase change memory to represent each weight layer, as we showed before, the weight representation is a lot noisier, and we are sometimes limited by the dynamic range of the phase change memory. So the perplexity with that mapping is a little higher. Note that even though this number is higher than the baseline, if we look at the perplexity range of similar models with the same number of weights, so here, this is still within the reasonable range for expected perplexity for this type of model. So obviously, the larger your model is, the lower the perplexity will go. But with this model size, this range is perfectly on target. And so what we show is that from 2 phase change memory to 4 phase change memory, we are able to close that perplexity gap. This is also why we didn't go in unlimited to like 8 PCM, 16 PCM, also because of the area constraint. So we believe that with today's programming strategy and today's phase change memory device, a 4 PCM unit cell would allow us to achieve software equivalent accuracy for inference. So with that, we want to address a important issue in phase change memory, which is conductance drift. So what is conductance drift? What that means is that, we have 2 phases, the amorphous and the crystalline state in the phase change memory. And it is the amorphous state that will gradually relax. And when it relaxes, it decreases the conductance slightly. So what that means is that the conductance, so here, the conductance you program at a certain time will gradually decrease over time with a slope that's characterized by the drift coefficient nu. So this process is well studied, and so it follows this equation. So the G naught and the T naught is the time you program and measure, and over time, it will decrease based on this formula. So the challenge here is that this new variable is not only causing the conductance to decrease, but it also varies from device to device. And even the same device, if you melt and quench, so you go through the reprogramming cycle one time, the new is going to change even for the same device. So the challenge is the mean new, so the speed, overall speed of this decay, and also the variation in new. So how do we tackle these 2 aspects? So in terms of the mean of the new, what we propose here is that we can have a global compensation factor at the output neuron, so as shown here. When we apply this activation function, nonlinear activation function, with the most popular ones being shown here, we can apply an amplification factor that counteracts the mean drift of the phase change memory. So as the conductance decrease over time, we know how long the time has passed, and we can amplify the signal based on the time. And what we have shown here is that when we apply this slope correction, the tolerance to this new mean, so the x-axis is the new mean, it becomes much greater. So the green dot here is a confined PCM model, and the red dot here is a mushroom PCM model. So what this shows here is that with the amount of new mean and also the standard deviation, the spread that we get, the devices today are going to be good enough for to counteract the drift. So in addition to applying the global scaling factor to compensate for the conductance decay, we can also do something on the neural network side. So this shows that for CNN, the effect is very similar. So if we apply slope correction, it's more tolerant to the new mean, while still sensitive to the spread in new sigma. However, if we increase the number of hidden layers, or we increase the size within each hidden layer. So what is shown here is that this is the 1-year accuracy drop. So for mushroom and for confined cell, you see an increase in the accuracy in both cases if we make the network larger. And finally, this is a paper that's just recently published in Nature Communications that showed that we can also play tricks when training the neural network, just add noise during the forward path. And be able to close the gap between the after transfer to PCM versus after training. So here you see the final program in PCM and training results becomes much closer when you take into account all the possible noise in the training phase. So finally, I want to talk briefly on the energy efficiency. So far we've talked heavily about what happens inside the tile, but in the end, the system is not going to be just the tile. We at least have the periphery and also the communication between the tile. So as mentioned at the beginning, parallelism is really the key. So if we can still choose with such a MAC unit to operate in a non-parallel fashion to, for example, avoid instantaneous current to be too high and so on. However, to get the power performance and throughput, we really need to design our circuitry as parallel as possible. And in order to achieve extreme power efficiency, some ideas that we propose in this paper, including avoiding ADC whenever possible. So we will transfer signals in analog duration and process directly in analog duration when possible. And then approximate the computations such as ReLU. ReLU is just getting rid of all the negative numbers also in analog domain, and be able to efficiently route the signal, because when we do the computation in memory, we still need to route the input and also the output to somewhere else. So if we are not careful in designing those components, eventually the bus and communication bottleneck will come back to limit the power efficiency too. So where are we on the roadmap in terms of power efficiency? Here is a plot of the teraops per second per watt. So power energy efficiency for most of the chips that is out there in the market today. We have the paper we show. Sorry, the paper we show is around 15 teraops per second per watt, which is here. We believe that this can be achieved in a couple of years with a reduced precision digital hardware, which is also an active area of research at IBM. However, we believe that we can get another 10x by the help of scaling and further reduction in conductance. So here are the way that we think we'll get that final 10x. The first is to reduce the conductance. So here you see that as the conductance decrease, So here is the actually decreasing scale. The power performance increase because the current you generate from the crossbar is lower and lower, and therefore the energy cost of each multiply and accumulate both decreases. Another important factor is in the technology node. So as technology node continue to decrease, the operations become much more energy efficient, and even the memory, any register memory you use also becomes much more energy efficient. So overall, we see that a improvement in both the analog element and the digital element will further bring the energy efficiency for this analog technology up. Okay, so in conclusion, in this talk, we've shown that non-volatile memory-based crossbar arrays can be used to map and accelerate deep neural network workloads. The goal here is to save power and time. We've shown that none of the memory is probably perfect. However, there are ways that we can make them work for both training and inference. For training, we've designed a new unit cell that utilizes capacitive devices to achieve software equivalent accuracy. For inference, we believe that with today's memory, maybe not only PCM, but if you use multiple memory for one unit cell, it is possible to achieve a software equivalent accuracy. We need to pay attention to the conductance drift, and also need to use extra techniques in terms of the training process. But for inference, the software equivalent accuracy is possible with analog memory today. Finally, we talk about energy projections, and as we go up higher and higher in the architecture outside of the analog tiles, we believe that the 100x speed up from the memory today, and maybe 10x speed up from very highly optimized reduced precision hardware is possible with analog memory technology. With that, I would like to acknowledge our group. Jeff Bird is the PI, Pritish Narayan, Stefano Ambrosio, Charles Mackin, An Chen, Katie Spoon, Bob Shelby, Koji Hosokawa, and Scott Lewis. With that, I will be happy to take any questions. Thank you.